Silence. Not the silence of a quiet room, the silence of a place with no air to carry sound at all. 15 billion miles from home. A single spacecraft smaller than a school bus drifts through the dark, carrying instruments older than most of the engineers who now monitor them. Its power is fading. Its transmitters send messages that take over 21 hours to reach Earth, one way. Its onboard computers run on less memory than a single low-resolution photograph. And then, one ordinary afternoon at NASA's Jet Propulsion Laboratory, an engineer looks at a string of numbers on a screen. They stop scrolling. They read it again. Because the numbers make no sense. This is the real story of Voyager 1, and the discovery no one at NASA expected to make. Stay with me. By the end of this, you'll understand why a 48-year-old machine, held together by outdated code and a shrinking power supply, may have just told us something new about the space between the stars, and you'll understand why the people responsible for that machine are choosing their words with unusual care. Let's go back to the beginning. September 5th, 1977, Cape Canaveral, Florida. A Titan Centaur rocket lifts off the pad, carrying a spacecraft with a single audacious purpose: to fly past the outer planets of the solar system and keep going, forever, into the unknown. Voyager 1 was never supposed to still be talking to us. Its primary mission, flybys of Jupiter and Saturn, was designed to last 4 years. 4 years on paper. That was the plan the engineers signed off on. That was the budget NASA approved. It has now operated for nearly half a century. Onboard engineers bolted a golden record to the spacecraft's frame. Sounds of Earth, greetings in 55 languages, music from Bach to Chuck Berry, photographs of children, oceans, mountains, and cities etched into copper and gold. A message in a bottle thrown into a cosmic ocean in case anyone or anything out there ever found it. But the golden record was never the mission's real achievement. The real achievement came later, much later, after Jupiter, after Saturn, after the cameras had been deliberately switched off to save power, and after most of the world had stopped paying attention to a spacecraft that, by the 1990s, seemed to belong more to history than to active science. 12 billion years. That's roughly how old the oldest light in the universe is, light that instruments like the James Webb Space Telescope now study routinely. Voyager 1's journey is nothing by comparison, in cosmic terms, and yet, in human terms, in terms of a single machine's endurance, it remains without precedent. On August 25, 2012, something happened that had never happened to a human-made object before. Voyager 1 crossed the heliopause. Here is what that means, and why it matters more than most people realize. Our sun does not just emit light and heat, it emits a constant outward wind of charged particles, the solar wind, that inflates a vast, invisible bubble around our entire solar system. Scientists call this bubble the heliosphere. Inside that bubble, everything is shaped by the sun, its magnetic field, its plasma density, its rhythm, rising and falling with an 11-year solar cycle that governs conditions across the entire solar system. Outside that bubble is something else entirely, the plasma left behind by other stars that died millions of years before our sun ever formed, cold, diffuse, ancient. Voyager 1 didn't just study the solar system anymore, it had left it. For the first time in human history, an object built by our own hands was sailing through the material of interstellar space itself, matter that predates the sun, predates Earth, predates every living thing that has ever existed on it. NASA confirmed the crossing using data from an instrument most people have never heard of, the plasma wave subsystem. It doesn't take pictures, it doesn't need to, it listens, it measures the density of the electrically charged particles around the spacecraft, translating invisible oscillations into something scientists can read as sound and data. When NASA released the very first recording of interstellar plasma in 2013, it sounded like nothing anyone expected. A low, eerie hum, rising and falling, generated not by anything alive, but by the ambient hiss of the galaxy itself. And it's this exact instrument, quiet, obscure, easily overlooked by anyone who isn't a specialist, that would go on to hand NASA its strangest readings yet, more than a decade later. But before we get there, we need to understand the scale of what's really at stake, because the numbers involved are almost impossible to hold in your head. Voyager 1 moves through space at roughly 38,000 miles per hour. That's about 17 kilometers every single second. At that speed, a trip that would take an airplane 16 minutes to complete, the length of a typical takeoff and climb, Voyager 1 completes in a fraction of a second. And yet, at that same blistering speed, it still takes tens of thousands of years for the spacecraft to reach the edge of the sun's gravitational influence, the outer boundary of the Oort cloud, a shell of icy debris that scientists believe marks the true gravitational edge of our solar system. Voyager 1 is fast beyond anything most of us can intuitively grasp, and it is still, by that measure, barely leaving the driveway. It carries less power today than a household refrigerator. Its plutonium generators lose about 4 watts of electricity every single year, forcing engineers on Earth to shut down instruments one by one just to keep the spacecraft alive. Not because the instruments have failed, but because there isn't enough power left to run all of them at once. By 2025, NASA had already powered down the cosmic ray subsystem, one of the last original instruments still transmitting data from beyond our solar system, an instrument that had operated continuously since before many of its current mission engineers were born. Every year, the list of working instruments gets shorter. Every year, the odds of hearing anything new from Voyager 1 again get smaller, which is exactly why what happened next stopped people in their tracks. Let's go chronological. Let's stack the facts, one date at a time, because the sequence matters just as much as any single discovery. November 2023, Voyager 1 suddenly starts transmitting gibberish, not silence, gibberish, a repeating pattern of ones and zeros that meant nothing to the engineering team back on Earth. For months, the spacecraft was, in the words of the mission team, talking but not saying anything we could understand. Imagine that for a moment. A voice reaching you from 15 billion miles away, clearly still speaking, clearly still trying, and utterly unintelligible. The cause, eventually traced by JPL engineers after weeks of painstaking diagnostic work, was a single corrupted chip in the flight data subsystem, a chip responsible for packaging science and engineering data before it's transmitted home. A tiny piece of 47-year-old hardware, degraded by decades of cosmic radiation exposure, had started scrambling the spacecraft's memory. The fix took months. Engineers had to relocate the affected code into unused sections of the computer's memory, sending commands that would take over 21 hours just to arrive, and another 21 hours before they'd know if it worked. Think about the patience that required. Every single test, every single command meant waiting nearly 2 full days for a single yes or no answer. No real-time debugging, no second attempt within the hour, just silence and waiting and hoping the next signal wouldn't be more gibberish. April 2024, communication is restored. It was treated rightly as something close to a miracle. A machine older than most of the engineers who fixed it, patched from over 15 billion miles away, using code written for computers with less processing power than a modern calculator. Engineering teams around the world took note. It became briefly one of the most quietly celebrated achievements in deep space history. Proof that a mission designed in the 1970s could still be saved by 21st century ingenuity, applied to hardware nobody currently working at NASA had ever been trained on directly. But then, in the months that followed, something else showed up in the restored data, something nobody on the team had been specifically looking for, something that had nothing to do with the chip, the memory, or the fix at all. The plasma wave readings weren't behaving the way the models predicted. Since 2012, scientists have watched the density of interstellar plasma around Voyager 1 slowly increase as the spacecraft moves farther from the sun's influence. That's expected. That's the model working correctly. Interstellar space, once you get deep enough into it, becomes gradually denser and more uniform, the way ripples on a pond smooth out the farther they travel from the point where a stone was dropped. Except Voyager 1's readings kept spiking. Brief, sharp increases in plasma density, followed by drops, in patterns that didn't match a smooth interstellar gradient at all. The first sign: localized plasma density waves, arriving in clusters, unconnected to any solar event that mission scientists could identify. Solar storms, when they occur, send detectable pressure waves outward through the heliosphere, waves that Voyager has recorded before, waves with a known signature. These new readings didn't match that signature. They came from a direction and with a timing that didn't correspond to anything happening back near the sun. The second sign: subtle shifts in the direction of the local magnetic field detected by Voyager's magnetometer that didn't align cleanly with the predicted structure of the heliopause boundary. For over a decade, the magnetic field data beyond the heliopause had behaved in a fairly consistent, well-modeled way. These new deviations were small, fractions of a degree, but persistent, showing up across multiple transmission windows rather than as a single glitch. The third sign, and the one that generated the most internal debate among the small circle of scientists with access to the raw data: a temperature reading in the surrounding plasma that came out higher than any existing interstellar medium model accounted for. Not by a small margin either. By enough that at least one internal analysis reportedly had to be rerun twice, on the assumption that a calculation error, not a real physical measurement, was the more likely explanation. It wasn't. Individually, each of these might be noise, instrument drift, the unavoidable static of asking a decades-old machine to measure something at the very edge of its designed capability, using sensors that were calibrated on a bench in California nearly 50 years ago and have never been recalibrated since, because there's no way to send a technician 15 billion miles to check. Together, though, they raised a question that a small number of scientists were willing to say out loud, carefully, and usually with several qualifiers attached. What if the boundary of our solar system isn't as smooth or as settled as we assumed? This is where a name enters the story: Dr. Jamie Rankin, a heliophysicist who has worked directly with Voyager data at Princeton and later NASA's Goddard Space Flight Center, has spent years studying exactly this transition zone, the place where the sun's influence fades and the galaxy's begins. Rankin and colleagues had already published research showing that the heliopause isn't a clean, static wall. It moves, it breathes, expanding and contracting with the rhythm of solar activity, sometimes by hundreds of millions of miles over the course of a single solar cycle. That alone was a significant revision to how the public, and even many scientists outside the field, had pictured the edge of the solar system. Not a hard boundary, like a national border on a map. Something closer to a tide line on a beach, constantly reshaped by forces pushing from both directions. Now, with Voyager's newest readings, a harder question follows. If the boundary itself is dynamic, unstable, reshaped by forces we can't directly observe from Earth, then everything we think we know about where our solar system ends may need to be rewritten, one Voyager transmission at a time. Some researchers have gone further still in more speculative discussions at scientific conferences rather than in peer-reviewed papers. They've raised the possibility that Voyager 1 may be detecting the outer influence of a nearby interstellar cloud structure our solar system is currently passing through, a region sometimes referred to by astronomers as the local interstellar cloud, or even the edge of a neighboring denser cloud complex the Sun is expected to encounter in the coming millennia. If that's what Voyager is brushing up against, decades ahead of predictions, it would mean interstellar space near our solar system is less like a calm, uniform sea and more like a coastline. Turbulent, layered, shaped by forces still being mapped, forces that no telescope on Earth, however powerful, can measure directly from a distance. It's a striking idea. It's the kind of idea that, if confirmed, would end up in astronomy textbooks within a decade. But it's not one the wider scientific community has accepted. Not yet. Maybe not ever. Here's the mainstream counterpoint, and it matters just as much as the mystery itself, because a story without this part isn't the whole story. Voyager 1 is not a young, precision-calibrated instrument. Its sensors have been exposed to nearly 50 years of cosmic radiation, extreme cold, and steadily declining power. Every reading it sends home today comes from hardware operating well outside its original design tolerances, monitored by software patched together, piece by piece, across 5 different decades of computing history. NASA's own Voyager team has been careful, publicly and repeatedly, to caution against over-interpreting short-term anomalies in the plasma wave data. Signal degradation, thermal noise introduced by the spacecraft's aging power systems, and the sheer difficulty of calibrating 47-year-old instruments from a distance of 15 billion miles all remain more probable explanations than a fundamental discovery about the shape of interstellar space. Linda Spilker, the mission's project scientist, has spent over 4 decades with this program, since before Voyager 1 even launched. Her position, echoed by much of the heliophysics community, is that every anomaly deserves rigorous patient verification against multiple instruments and multiple data passes before any conclusion is drawn. There's a reason for that caution beyond simple scientific conservatism. Voyager has produced false alarms before. In the early 2010s, ahead of the confirmed 2012 heliopause crossing, several transient readings briefly suggested the spacecraft had already left the solar system, readings that, on closer inspection, turned out to be temporary fluctuations within the heliosphere itself, not a true crossing at all. The lesson from that experience shaped how today's team treats every new anomaly, with excitement, but not with premature announcement. That verification is exactly what's happening right now, quietly, without headlines. Teams are cross-referencing Voyager 1's readings against Voyager 2, its twin, traveling in a different direction on the opposite side of the solar system, to see whether the same plasma disturbances show up there too. If they do, the anomaly likely reflects something real about the structure of interstellar space itself, something present on multiple independent flight paths rather than isolated to one aging spacecraft. If they don't, the more probable explanation is a spacecraft, one of the oldest functioning machines humanity has ever built, finally showing its age on one specific set of instruments in one specific location, unconnected to any wider phenomenon. Both outcomes, in their own way, are extraordinary, because here's what almost nobody talks about, and it's worth pausing on. Even the boring explanation is astonishing. A machine launched during the Ford administration, running on computer systems with less memory than a single modern text message, is still sending back usable scientific data from a region of space no other operational spacecraft has ever reached. Everything changed the moment Voyager 1 crossed that boundary in 2012, not just for the mission, but for what it meant to be a spacefaring species. Before that date, every measurement humanity had ever made of interstellar space was indirect, telescopes gathering light from a distance, models built on assumption and extrapolation. After that date, for the first time, we had a direct witness. Voyager 2 is the only other human-made object to have crossed into interstellar space, doing so in November 2018, 6 years after its twin, along a completely different trajectory, exiting the heliosphere from a different direction entirely. Together, the two Voyagers remain the only direct in-place sensors humanity has ever had beyond the edge of the sun's influence. Everything else we know about interstellar space, every textbook diagram, every simulation, every model of the heliopause, is built on inference. Telescopes looking from a distance, physics extrapolated from observations of other stars and their own stellar winds. The Voyagers are the only instruments that have actually been there, touching it, measuring it directly, one data point at a time, as they drift farther from home than anything we've ever built. And that's precisely why even a single unexpected reading carries enormous scientific weight. There is no backup mission. There is no second flyby scheduled. There is no way to send anything else out to check, not in any time frame that matters to a single human lifetime, and not with any spacecraft currently funded or under construction. NASA has studied concepts for an interstellar probe, a proposed future mission designed explicitly to travel faster and farther than the Voyagers, carrying modern instruments specifically built for this environment. But that mission, even under the most optimistic timelines discussed in mission concept studies, wouldn't launch before the 2030s and wouldn't reach interstellar space for decades after that. Which means whatever Voyager 1 measures in the coming years may be the only direct data humanity ever collects from this exact region of space, possibly for generations, possibly for longer than that. NASA has confirmed that both Voyagers are expected to lose the power required to operate any scientific instruments sometime in the early 2030s, as their plutonium power sources continue to decay past the threshold needed to keep instruments running. After that, the spacecraft won't die, they'll simply go silent, continuing to drift forever, carrying the golden record and its message from a civilization that, by the time anyone finds it, may look nothing like the one that built it. Let that settle for a moment. Every message Voyager 1 has ever sent, every discovery it has ever enabled, has come from a window of time that is now visibly, measurably closing. The plasma anomalies detected in 2024 and debated through 2025 may be among the very last genuinely new discoveries this specific spacecraft is capable of making before its instruments go dark for good. Which brings us to the deeper question sitting underneath all of this, a question about time itself and about what it actually means to witness something happening now. Everything you're seeing in Voyager's transmissions right now is old. Because it takes light, and radio signals travel at the speed of light, over 21 hours to cross the distance between Voyager 1 and Earth, every anomaly, every plasma spike, every strange reading in this story already happened nearly a full day before anyone at NASA ever saw it. We are not watching interstellar space in real time. We are reading a message written in the past, about a region of the galaxy no living scientist has ever directly touched, decoded by a machine that is, quite literally, running out of power to keep telling us what it finds. And there's a stranger layer underneath even that. The interstellar plasma Voyager 1 is currently measuring isn't new material either. Scientists believe much of the plasma in this region formed from the remnants of stars that lived and died long before our own sun ignited, material that has been drifting through the galaxy, largely undisturbed for potentially millions of years, only now brushing past a small, aging spacecraft built by a species that didn't exist for almost all of that time. In a very real sense, Voyager 1 isn't just exploring distant space. It's reading a kind of galactic history, a plasma that predates humanity, predates Earth's current geological era, predates the Sun's own planetary system in its current form, and it's doing so with instruments that are themselves now approaching the end of their functional lives. Nobody expected a 47-year-old spacecraft to still be rewriting textbooks. Nobody expected the edge of our solar system to look less like a wall and more like a shoreline. And nobody expected that the answer, if there is one, would come not from a new billion-dollar telescope, but from a machine built before most of its current mission engineers were even born. Whether Voyager 1 has genuinely detected the turbulent edge of a nearby interstellar cloud, or whether we're witnessing the graceful expected decline of aging hardware at the absolute limit of its endurance, one thing is no longer in question. We built something that outlived every expectation placed on it and sent it further into the dark than anything else we've ever made, and it is still, after all these years, finding things we didn't know. Meanwhile, back on Earth, the team responsible for keeping that signal alive keeps shrinking too. Many of the original Voyager engineers have retired or passed away in the decades since launch. The current mission team is largely made up of scientists and engineers who joined the project years, sometimes decades after it began, inheriting a spacecraft and a body of undocumented institutional knowledge that grows harder to fully understand with each passing year. When researchers looked again at the earliest Voyager engineering logs from the 1970s, hunting for clues about how certain systems were originally designed to behave, they found handwritten notes, faded documentation, and design decisions that made sense only in the context of hardware limitations that no longer exist anywhere else in active use. Understanding Voyager 1 today means understanding not just physics, but the working assumptions of engineers who assumed no one would ever need this information again. And yet someone did, decades later, 15 billion miles away. With the fate of humanity's furthest reaching machine hanging on, whether that knowledge could be recovered in time. Somewhere out there, past the reach of sunlight, past the boundary that used to mark the edge of everything we called home, a spacecraft the size of a small car keeps sending its signal back toward a planet it will never see again. And somewhere, on the other end, scientists keep listening, because as long as Voyager 1 keeps talking, the story of what actually lies beyond our sun's reach is still being written. By the end of the 2020s, both Voyagers will likely fall silent for good. Every dataset from that point forward will be historical, not active, a closed archive rather than a living conversation. Whatever remains unresolved about these plasma anomalies when that silence finally falls may stay unresolved, at least until humanity builds something capable of reaching that same region of space again, a project that, right now, exists only as a proposal on paper. That's the quiet urgency underneath every strange reading in this story. Not just curiosity about what's out there, but the awareness that the window to ask is closing, watt by watt, year by year, and there may not be another spacecraft in position to pick up the question for a very long time after Voyager 1 finally goes quiet. If you want to go deeper into the mystery of what lies past the heliopause and what Voyager 2's twin readings might already be telling us, that's a story for next time. Subscribe so you don't miss it.